welcome to Next Worldwide. Glad you're here tonight. Maybe your day ran long. Maybe your mind is still buzzing and you need something to slowly pull it away from the noise. Either way, you're in the right place. Tonight, we're not counting sheep. We're drifting through the Milky Way, our home galaxy. A massive spiral of stars, ancient gas clouds, and invisible forces that has been quietly spinning for more than 13 billion years. Beneath its beauty is a story full of surprises. Wandering stars, hidden collisions, forces we still can't fully explain, and a history that stretches back almost to the beginning of time. We'll move gently from the outer spiral arms to the mysterious core, from regions where stars are being born right now to places where stars were flung out of the galaxy entirely. Some of what you hear tonight might genuinely surprise you. All of it is real. Before we begin, if these kinds of slow, science-driven journeys help you to unwind at night, consider subscribing to Next Worldwide. It helps more people find their way here. Now let's go. The Milky Way has already swallowed other galaxies, and it will again. Our galaxy might feel like stable ground, but it's actually a composite, assembled over billions of years from smaller systems it drew in and dismantled. The wreckage of those older galaxies is still visible today in the form of stellar streams. Long ribbons of stars draped around the galactic disk. One of those galaxies, the Sagittarius dwarf, is still being pulled apart in slow motion right now. Another, far larger, is approaching. The Andromeda galaxy, our nearest major neighbor, is on a direct collision course with the Milky Way. In about 4.5 billion years, the two spirals will meet. Stars are too widely spaced to physically crash into each other, but the shapes of both galaxies will be permanently altered, folding into something entirely new. Even galaxies aren't permanent. They build, merge, and start over. Some stars in the Milky Way predate the galaxy they live in. In the outer halo, the diffuse spherical region surrounding the galactic disk. Astronomers have found ancient stars with almost no heavy elements in their composition. These stars carry the chemical fingerprint of a universe that had barely begun to evolve. No iron, little calcium, almost nothing beyond hydrogen and helium. They formed before the Milky Way had assembled into a spiral born from primordial gas in small early galaxies that were later absorbed. They drift in long tilted orbits far above the galactic plane. Quiet elders from a time before structure, before spirals, before anything we'd recognize as home. Right now, our solar system is moving through the galaxy at more than 800,000 kilometers per hour. That's roughly 230 kilometers every single second. And yet, even at that speed, it takes about 225 million years to complete one full orbit around the galactic center. That journey is called a galactosphere. In the entire 4.6 billion year history of our solar system, we've only gone around the Milky Way roughly 20 times. The last time we were in this same part of the galaxy, the supercontinent Pangaea had just begun to break apart. Dinosaurs had not yet evolved. Every star you see tonight is in a different position than it was then. Everything is moving. Everything always has been. The Milky Way is ancient, but it isn't finished. Even now, it continues to accumulate material. Thin streams of gas fallen from the space between galaxies. Dwarf satellite galaxies drift too close, get caught in the gravitational pull, and are slowly torn apart. They're star-scattered into the halo. Dark matter continues to feed the galaxy's outer structure in ways we can measure but not directly see. The Milky Way of today is larger and heavier than the one that existed when the first complex life appeared on Earth. And the version that exists billions of years from now will be larger still. Stitched together from the remains of smaller worlds absorbed one by one across cosmic time. Here's something that should be surprising. We don't know exactly how many-spiral arms the Milky Way has. From our position embedded inside the galactic disk, it's nearly impossible to see the full structure. Thick dust clouds block our line of sight. Stars in distant regions blur together. For decades, the standard picture showed 4 major arms. More recent observations have complicated that. Some apparent arms fade into fragments. Others split or curve in unexpected ways, and the overall shape may be less like a neat pinwheel and more like a layered swirl with no clean boundaries. We live inside the thing we're trying to map. That makes it extraordinarily difficult. Deep in the galactic center, near the supermassive black hole, pairs of stars occasionally drift too close. The black hole's gravity disrupts their shared orbit. One star is captured. The other is hurled outward at incredible speed, sometimes faster than 1,000,000 kilometers per hour. Fast enough to escape the Milky Way entirely, these are called hypervelocity stars, and they travel alone through intergalactic space, carrying with them no companions, no destination. They're flung relics of gravitational disruption, glowing in the dark between galaxies. Even in a system defined by gravity's hold, some things break free. High in the northern sky, barely visible to the naked eye as a faint smudge of light, is the Andromeda galaxy. Our largest galactic neighbor, located over 2 million light-years away. It is moving toward us. In roughly 4.5 billion years, the Milky Way and Andromeda will collide. But this won't look like a catastrophe in any familiar sense. Stars are spaced too far apart for direct collision to be common. What will happen instead, it is a slow gravitational ballet. The two spirals will stretch, warp, and loop into long tidal arcs. The central black holes may eventually spiral toward each other. Over billions of years, the two galaxies will merge into a single, larger elliptical system. It will be slow. It will be total. And it will be the end of both galaxies as we know them, and the beginning of something else entirely. Most stars in the Milky Way travel in the same general direction as the galaxy rotates, but not all of them. Some stars, particularly in the outer halo, orbit in the opposite direction, moving retrograde against the galactic flow. These are almost certainly stars that were born elsewhere. They came from dwarf galaxies absorbed by the Milky Way long ago, and their reversed motion is a quite signature of that foreign origin. The galaxy carries its history in motion, not just in light or chemistry, but in the direction stars turn. Every star is born with a specific chemical composition, a fingerprint determined by the gas cloud it formed within. By analyzing what elements are present in a star's atmosphere and in what proportions, astronomers can trace where it likely came from and when stars rich in iron and calcium formed in dense chemically evolved environments. Stars with almost nothing beyond hydrogen and helium are ancient, born when the universe had not yet generated the heavier elements through stellar fusion and supernovae. These chemical fingerprints let scientists identify stars from ancient merged galaxies, reconstruct the Milky Way's formation history, and in some cases identify groups of stars that were once part of the same birth cloud millions or billions of years ago. Chemistry becomes archaeology. Light becomes memory, traced carefully across the sky. Astronomers have found thin arcs and ribbon-soft stars stretching across vast distances. These are stellar streams, the remains of smaller galaxies and star clusters that passed too close to the Milky Way and were pulled apart by tidal forces. As these systems orbited, the galaxy's gravitational pull stretched them, smearing their stars along long, graceful curves. Some streams wrap nearly all the way around the galaxy. Others fall inward toward the core. Each one is evidence of an ancient merger. A smaller world absorbed, its stars scattered into the Milky Way's halo like the residue of a story that ended 1 billion years ago. The Milky Way doesn't lie flat. Its disk bends, upward on one side, downward on the other, in a gentle wave that can only be mapped with radio telescopes, tracking hydrogen gas far beyond the visible stars. The cause of this warp is still debated. Some models point to gravitational tugging from satellite galaxies at the edges. Others suggest clumps of dark matter bending the disk from below. Whatever the cause, the effect is clear. Even the Milky Way itself is not perfectly stable. Over cosmic time, it bends, adjusts, and continues turning. A great spinning sheet that ripples as it moves. On the clearest, darkest night, far from any city, you might see several thousand individual stars. That feels like a lot. It is almost nothing. The Milky Way is estimated to contain somewhere between 100 billion and 400 billion stars. The few thousand visible to the naked eye represent a fraction of the total. Most are hidden behind dust. Others are too dim or too distant. The pale band crossing the night sky is just the innermost whisper of the disk, a tiny sample of something vastly larger. We are surrounded by an ocean of light. Almost all of it is invisible to us. Stars in the Milky Way don't all orbit at the same speed. Those closer to the center completing their orbits more quickly. Those in the outer disk move more slowly. This difference in orbital speed creates a natural tendency toward pattern formation. Density waves, regions of slightly higher stellar concentration, propagate through the disk like slow ripples in a pond. As gas and dust enter these denser regions, they get compressed and collapse into new stars. Those bright young stars then light up the wave's position, making it visible as a spiral arm. The arms aren't solid structures. Stars drift through them and keep moving. What we see as an arm is more like a standing wave. A pattern, not a fixed arrangement of the same stars. By all the rules of physics we understand, the Milky Way should not hold together the way it does. The stars in the outer disk orbit far too quickly. At their speed, they should be flung outward, but they aren't. Something is holding the galaxy together. Something that doesn't emit light, doesn't absorb it, and can't be directly detected by any instrument we've yet built. This is dark matter. It outweighs all the visible stars, gas, and dust in the galaxy by a large margin. We don't know what it's made of. We can't see it or touch it. But we know it's there because of what it does to everything around it. The Milky Way floats inside a vast halo of something we cannot name, held together by gravity from a source we can't observe. That's not a gap in the data. That's one of the central open questions of modern physics. At the precise center of the Milky Way sits an object containing more than 4 million times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. This is Sagittarius A, our galaxy's supermassive black hole. We can't photograph it directly in visible light. Thick curtains of dust and gas block our view. But astronomers have tracked nearby stars for decades, watching them whip around an invisible point at tremendous speeds, tracing tight ellipses through the void. Right now, Sagittarius A is quiet, but evidence suggests it wasn't always. Long ago, it may have blazed like a quasar, one of the brightest, most energetic objects in the universe, pouring radiation outward from the galaxy's heart. Those days appear to be over. For now, the center sleeps. When astronomers mapped the central bulge of the Milky Way in infrared light, they found something they didn't expect. The bulge isn't round, it's shaped like a peanut, swollen in the middle, narrowed at the ends, twisted along its length. This unusual shape likely formed from a process involving the central bar, a dense, elongated concentration of stars that crosses the core of the galaxy. Over billions of years, gravitational resonance between the bar and stellar orbits caused the structure to buckle vertically, puffing upward and downward into the shape we now observe. The center of our galaxy is not flat or simple. It's a three-dimensional structure built by billions of years of internal dynamics. The Milky Way's spiral arms aren't just populated by stars. They're where stars come from. Enormous molecular clouds, composed mostly of hydrogen gas and trace amounts of dust drift through the galactic disk. When these clouds enter a spiral arm and encounter the region's higher density, they get compressed. That compression triggers gravitational collapse within the cloud. Pockets of gas fall inward, heat up, spin faster, and eventually reach the temperatures and pressures required for nuclear fusion to ignite. A new star begins. The regions where this happens are called stellar nurseries, spreased, chaotic, luminous, and full of motion. The most massive new stars pour out intense ultraviolet radiation that ionizes the surrounding gas, causing it to glow. That glow traces the spiral arms, illuminating the galaxy's curves with light from suns that didn't exist a few million years ago. Beyond the disk, above and below the spinning plane of stars, lies halo. It's a vast, diffuse spherical structure surrounding the entire galaxy, and it contains almost no bright young stars. What it does contain is ancient, globular clusters, tight spheres of hundreds of thousands of stars bound tightly by gravity. Drift through the halo in long, slow orbits. Some are more than 12 billion years old. Many contain stars that predate the formation of the galactic disk itself. Their chemical compositions are simple, almost no heavy elements, confirming that they formed very early, before successive generations of stars had seeded the galaxy with the heavier material. The halo also holds stellar streams from dismantled dwarf galaxies. And most importantly, it holds the vast majority of the Milky Way's dark matter mass. The disk is where things happen. The halo is where the galaxy's memory lives. In the early universe, galaxies were far more active, burst after burst of rapid star formation, fueled by abundant cold gas. Our galaxy was no exception. It once formed stars at a much higher rate than it does today. Over billions of years, that activity has declined. Not because the gas is gone entirely, but because much of it has been heated, spread too thin, or locked into structures that don't collapse easily. The remaining cold gas collapses more slowly, forms fewer stars per unit time, and the pacing of new creation has settled into something more restrained. We live in what astronomers might call the Milky Way's middle age. Still forming stars, still changing, but no longer in the explosive early phase. The galaxy has settled into a slower rhythm. According to standard gravitational physics, stars at the outer edges of a galaxy should orbit more slowly than those near the center, just as the outer planets in our solar system orbit more slowly than the inner ones. But in the Milky Way, that's not what we observe. Stars in the outer disk move at roughly the same orbital speed as those much closer to the center. The rotation curve is nearly flat when it should decline. This is one of the strongest pieces of evidence for dark matter. The only way to reconcile the observed speeds with gravitational physics is to assume that a large invisible mass is distributed throughout the halo, adding gravitational pull to the outer regions. Remove that invisible mass, and the math stops working. The galaxy rotates in a way that only makes sense if most of it is hidden. Scattered throughout the disk are enormous molecular clouds, dark, cold, and vast. Some span hundreds of light years. They're composed mostly of molecular hydrogen, with traces of carbon monoxide, dust, and more complex molecules. These clouds are so cold, just a few degrees above absolute zero, that they emit almost no visible light. In optical images, they appear as dark patches blocking the stars behind them. But viewed in radio wavelengths or infrared, they reveal their structure. Dense filaments, layered region-soft collapse, and pockets of gas on the verge of becoming stars. They are the galaxy's raw material. Everything that will ever burn a star in the future is currently sitting in one of these dark, silent clouds, waiting. When a massive star exhausts its fuel, it collapses and then explodes in a supernova, releasing more energy in a few seconds than the sun will radiate across its entire lifetime. These explosions don't just end stars. They reshape the galaxy around them. The shockwave blasts outward through the interstellar medium, compressing nearby gas clouds and potentially triggering new waves of star formation in the process. The explosion also scatters heavy elements, iron, calcium, oxygen, and more, that were forged in the dying star's core. Those elements get incorporated into future star systems, future planets, and eventually into living things. Supernovae are the Milky Way's moments of violent renewal, destructive, radiant, and necessary to the cycle. Interstellar dust, microscopic grains of carbon, silicates, and ices, weaves through the galaxy in clouds and tendrils. In visible light, it's nearly opaque. Entire regions of the galaxy, including vast star-forming zones, are hidden behind it. But dust isn't just an obstacle. It plays an active role in stellar birth. It helps gas cool. It shields newly forming stars from radiation that might otherwise disrupt collapse. It carries complex organic molecules, carbon compounds, water ice, even simple amino acid precursors that may eventually find their way into the chemistry of planets. What looks like darkness from the outside is often a nursery inside. Stars are not permanent. They burn through their fuel over millions or billions of years. And when they run out, they die. But the material they were made of doesn't disappear. It goes back. Red giants shed their outer layers gently into the surrounding medium. Planetary nebulae drift outward like slow, glowing halos. Supernovae scatter their enriched material across light years in a single explosive moment. That returned material mixes with existing gas in the interstellar medium. It cools, it condenses, it forms new clouds. Eventually, those clouds collapse into new stars and new planetary systems. And those planets may form the conditions for life. And that life may contain atoms that once burned in a star that died before the sun was born. The galaxy breathes. It inhales its past and exhales a new beginning. In astronomy, any element heavier than helium is called a metal. The earliest stars in the universe formed when almost no such metals existed. The Big Bang produced only hydrogen, helium, and trace lithium. Everything heavier elements had to be made inside stars. The most ancient stars still observable today, found mostly in the galactic halo. contain almost none of these heavier elements. They formed before earlier stellar generations had time to enrich the galaxy. Some contain iron levels less than 1/100,000th of what the Sun has. These stars are extraordinary archives. By reading their composition, astronomers look back toward the universe's earliest epochs, a time before galaxies had fully assembled, when conditions were raw and everything thievier than helium had yet to be created. They are fossils made of light, still burning. A star's birthplace is not its permanent address. Over time, gravitational interactions with other stars, encounters with dense molecular clouds, and the passage of spiral arms all shift stellar orbits. Some stars migrate slowly inward toward the galactic center. Others drift outward into quieter regions. A few are scattered to dramatically different orbits by close encounters or disruptions in binary systems. Our own Sun is probably not where it started. Astronomers estimate it may have formed somewhat closer to the galactic center and migrated outward over billions of years. The siblings it was born alongside have long since scattered, drifting in different directions, following orbits shaped by 4.5 billion years of galactic experience. Just as Earth sits in a habitable zone around the Sun, not too hot, not too cold, astronomers have proposed that the galaxy itself has a habitable zone, a band of conditions more favorable to the development of complex life. The inner regions near the galactic core are hostile. Intense radiation, a crowded stellar environment, frequent gravitational disruptions, and high rates of supernovae that would regularly sterilize nearby worlds. The outer regions are too sparse and chemically primitive, lacking the helivier elements that form planets and living things. In between lies a zone where stellar density is moderate, chemical enrichment is sufficient, and the radiation environment is manageable. The Sun orbits within this zone. That may not be a coincidence. One of the most visually striking features of a spiral galaxy, the arms themselves, are not solid structures. They are density waves, regions of slightly elevated concentration that move through the disk at their own speed, independent of the individual stars. As stars, gas, and dust drift into one of these denser regions, the crowding triggers new star formation. Bright young stars light up the arm's location. Then those stars drift out the other side, and the pattern moves on to compress the next section of gas. From a distance, it looks like a fixed structure. From within, it's a moving pattern, like a slow wave rolling through a field of wheat, with no single stalk staying elevated for long. Beyond the light we can see with our eyes, the Milky Way radiates across the entire electromagnetic spectrum. X-rays stream from the cores of neutron stars and the edges of black holes. Radio waves pulse from spinning pulsars and drift from cold hydrogen clouds. Gamma rays emanate from energetic collisions and decay processes throughout the disk. And everywhere, in every direction, cosmic rays stream through space. These are high-energy particles, mostly protons, accelerated to near-light speed by supernovae and other extreme events. They travel through the galaxy, bend through magnetic fields, pass through gas clouds, and eventually pass through you. The galaxy is not a place of quiet starlight. It is an active, multi-frequency environment that we only partially perceive. Every second, it touches you in ways you can't feel. In 2010, astronomers made an extraordinary discovery: two enormous structures, lobes of high-energy gamma-ray emission, stretching roughly 25,000 light-years above and below the galactic center. They are called the Fermi bubbles. No one is entirely sure what produced them. The leading explanations point either to a massive outburst from Sagittarius A millions of years ago, or to an unusually intense episode of star formation near the galactic center that collectively generated enough energy to blast material outward through the disk. Whatever their cause, the Fermi bubbles are real, and they are enormous. They extend far above and below the galaxy's visible plane, invisible to the human eye, detectable only in high-energy light. Twin echoes of something that happened long ago near the center of everything we call home. Our solar system doesn't sit in one of the Milky Way's major spiral arms. We occupy a smaller, less dramatic structure called the Orion Spur, a lane of stars nestled between the larger Sagittarius arm inward and the Perseus arm outward. It's not a glamorous address, but it may be an important one. In the quieter in the space between major arms, supernovae are rarer. Radiation storms are less frequent. Gravitational disturbances are more moderate. Life on Earth has shod billions of years in a relatively stable neighborhood to grow increasingly complex without being periodically reset by catastrophic events from nearby. Our location in the galaxy may be less random than it seems when astronomers examine the core of the Milky Way in infrared light. Wavelengths that penetrate the dust, they find a thick, elongated Barov stars crossing the central region. It extends roughly 27,000 light-years from end to end. This bar rotates slowly as a unit and has a profound effect on the inner galaxy. It channels gas inward toward the central regions, potentially feeding the supermassive black hole. It shapes the orbits of nearby stars. It drives the formation of the inner spiral arms. Bars are common in spiral galaxies. More than half of all known spiral shape them. The Milky Way's bar makes it a barred spiral. Though from inside, we only discovered this in the last few decades. The Milky Way is not alone in its region of space. It belongs to a collection of more than 50 galaxies called the Local Group, a loose gravitational family spanning roughly 10 million light-years. The two largest members are the Milky Way and Andromeda, each surrounded by their own satellite galaxies. The rest are mostly small, dim dwarf galaxies, some with barely any stars at all, consisting mainly of dark matter and trace gas. The members of the Local Group are gravitationally bound. They are not flying apart from each other like most distant galaxies in an expanding universe. Some orbit the Milky Way directly. Others drift on slower, more independent paths. Over billions of years, the group will likely consolidate further. Galaxies merging, satellites being absorbed, the family condensing into something different. The Milky Way's disk isn't a single uniform layer. It has structure. The thin disk, where the Sun lives, is a dense flat plane roughly 1,000 light-years deep. It contains young stars, open clusters, and active star-forming regions. Most of the galaxy's visible activity happens here. Above and below it lies the thick disk, older, puffier, and more chemically primitive. Stars in the thick disk tend to have fewer heavy elements, move in more tilted orbits, and belong to older stellar populations. They likely formed during an earlier, more turbulent phase of galactic history, perhaps stirred into their current configuration by an ancient collision. The disk you can see is a thin slice of something layered and complex. Threading through the disk and halo is something invisible but structurally important. The Milky Way's large-scale magnetic field, it's too weak to be felt. Far weaker than a refrigerator magnet, but across galactic distances, it matters. It influences how cosmic rays travel through the galaxy. It affects the alignment of dust grains, which in turn shapes how light is polarized. It may influence whether gas clouds collapse into stars or resist collapse. It rises in arcs above the galactic planion, forms complex loops whose origins are still debated. The Milky Way is not just a gravitational and optical structure. It is a magnetized environment, threaded with invisible lines of influence that reach across tens of thousands of light years. Between every star in the Milky Way lies what we sometimes casually call empty space. It is not empty. The interstellar medium fills this space with a thin mixture of gas, dust, and charged particles. It forms filaments and bubbles, compressed regions, and vast low-density cavities. Supernovae carve enormous hollows through it. Stellar winds sculpt it into shapes that span light years. Magnetic fields thread through it. Temperature variations within it can range from near absolute zero in cold molecular clouds to millions of degrees in the vicinity of recent supernovae. The space between the stars is not a void. It's a dynamic, turbulent sea, the reservoir from which everything is eventually made. Planets don't always stay attached to stars. During the formation of a planetary system, gravitational interactions between multiple young planets can fling some of them outward, expelled from the system before they ever settle into a stable orbit. These become rogue planets, worlds drifting through interstellar space, attached tonostar, receiving no starlight. Current estimates suggest the Milky Way may contain billions of these wandering worlds, some in the disk, others in the outer halo. They are extraordinarily difficult to detect, lit only by the faint heat of Theround interiors. But they exist, Cold and quiet, following slow paths through the dark spaces between stars. Some worlds never get a sun. They just drift. When two neutron stars, the collapsed cores of once massive stars, spiral toward each other and finally merge, the result is called a kilonova. In that brief blinding collision, conditions of temperature and pressure exist that are capable of forging the heaviest elements in the periodic table: gold, platinum, uranium, barium. Elements that ordinary stellar fusion cannot produce are created in quantity during these rare events, and then scattered into surrounding space by the explosion. Some of the stars we observe in the Milky Way carry the chemical signature of these ancient collisions, enriched in elements that could only have come from a kilonova. They are not just stars. They are records inscribed with the residue of some of the most violent events the galaxy has ever witnessed. The gold in any ring anyone has ever worn was forged in a neutron star collision. Above and below the Milky Way's disk, something slow and important is happening. Massive stars explode. Their combined winds and supernovae heat enormously, quantities of gas, and eject it upward out of the disk and into the halo. There, far above the galactic plane, the gas cools over millions of years and eventually rains back down. This process, called the galactic fountain, cycles material continuously between the disk and the halo. It redistributes the heavy elements forged in stellar explosions across broader regions of the galaxy. It helps regulate the pressure and temperature of the interstellar medium. It sustains the conditions in which future generations of stars can form. The galaxy breathes, slowly, in cycles that span tens of millions of years. Inside the dust clouds that drift through the Milky Way, astronomers have detected complex organic molecules. Carbon-based compounds, simple sugars, alcohols, structures that are not alive but are chemically related to the building blocks of life. These molecules form in the outer layers of dying stars and within cold interstellar clouds where starlight and chemical reactions gradually build complexity. They're carried through the galaxy on grains of dust and incorporated into the gas clouds that eventually collapse into new solar systems. When a planet forms, it may inherit some of this chemistry delivered by comets and asteroids that formed from the same primordial cloud. The Milky Way may be seeding its planetary systems with the raw ingredients of biology scattered across trillions of kilometers of space. The Sun completes one full orbit around the Milky Way roughly every 225 to 250 million years. That duration is called a galactic year. It's a unit of time almost impossible to feel. In the last galactic year, the entire Mesozoic era, the age of the dinosaurs, unfolded and ended. Continental plates drifted into positions unrecognizable from what they are today. Multiple mass extinction events occurred in the full 6 billion year lifetime of the solar system. We have completed fewer than 21 orbits. We are a young solar system in an old galaxy, still early in our journey around the center. The last time we were in this exact part of the galaxy, our species did not exist. The Vittel from the southern hemisphere as bright smudges of light. The large and small Magellanic Clouds are two irregular dwarf galaxies that have long been considered satellites of the Milky Way. But recent data suggests something surprising. They may be on their first close approach. Their velocities, when measured carefully, suggest they may be moving too fast to have been in stable orbit around the Milky Way for billions of years. This first pass, if confirmed, changes our understanding of their history. They are not longtime companions. They may be newcomers, falling under the Milky Way's gravitational influence for the very first time. Their passage has already visibly distorted the outer disk of the galaxy. The Milky Way is responding to their arrival. Trailing behind the Magellanic Clouds is a structure called the Magellanic Stream, a vast ribbon of hydrogen gas spanning hundreds of thousands of light years across the southern sky. It's invisible in optical light, but bright in radio wavelengths. It was drawn out by tidal forces as the dwarf galaxies passed each other and moved close to the Milky Way. Stars follow paths, but gas can be stripped more easily, and the Magellanic Stream is the evidence of that stripping. A long, curving wake of material pulled away during a gravitational encounter. This stream may eventually fall into the Milky Way's disk, feeding future star formation with fresh hydrogen gas from beyond the galaxy's boundaries. As the Sun orbits the galactic center, it doesn't travel in a perfectly flat line. It oscillates, drifting above the galactic plane, crossing back through it, descending below, and rising again. The cycle takes roughly 60 to 70 milliseconds years per half oscillation. This gentle wave is caused by the gravitational pull of the galaxy's mass distribution. As the Sun moves above the plane, gravity pulls it back. As it crosses and moves below, gravity pulls it back again, like Aslow wide pendulum. Some researchers have asked whether this oscillation correlates with patterns in Earth's geological record, such as cycles of increased meteor impacts or extinction events. The evidence is not clear, but the motion itself is real. Even on its steady journey around the galaxy, the Sun is also gently, continuously rising and falling. When a massive star exhausts its fuel and its core collapses, the result is sometimes a neutron star, an object packing more mass than the Sunninto, a sphere only about 20 kilometers across. If that neutron star is spinning rapidly and emitting beams of radiation, we call it a pulsar. Some pulsars complete hundreds of rotations per second. They are extraordinarily precise, among the most accurate natural timekeepers in the universe. Astronomers use them to test the predictions of general relativity, to measure distances across the galaxy, and to search for gravitational waves by monitoring slight timing variations over years and decades. They are the remains of death, repurposed into something useful. Remnants off a cataclysm, ticking steadily in the dark, much of the Milky Way is invisible in optical light. Dust blocks it, distance dims it, but radio waves pass through almost everything. By mapping the galaxy in radio wavelengths, particularly the 21-centimeter emission line from neutral hydrogen, astronomers have been able to trace distribution of gas across the entire disk. They've mapped the spiral arms, measured the warp, identified star-forming regions hidden behind PAPOC dust clouds, and discovered large-scale structures that would be completely invisible. Otherwise, the galaxy has a version of itself that exists entirely in radio, and it looks different from the optical one. Structures appear that have no visible counterpart. Processes are revealed that optical telescopes cannot show. We map the galaxy in many languages. Radio is one of the most informative. The Sun wasn't born alone. Stars form in clusters, groups of hundreds to thousands of stars, all collapsing from the same gas cloud at roughly the same time. The Sun almost certainly had siblings, stars born alongside it in the same cloud, sharing a common chemical composition and a common starting point. That cluster has long since dissolved. The Milky Way's tidal forces and internal gravitational interactions gradually pulled the cluster apart over hundreds of millions of years. The Sun's siblings scattered, drifting into different orbits, spreading across the galaxy, following their own separate paths for the last 4 billion years. Using data from surveys like the Gaia mission, astronomers are searching for them. Stars with the right age, the right chemical fingerprint, the right motion. A few candidates have been identified. The Sun's family is out there, somewhere in the galaxy. We just haven't found most of them yet. You might expect that we would know the mass of our own galaxy with reasonable precision. We don't. Measuring it requires tracking how objects at different distances from the center behaves gravitationally. The farther out you look, the harder this becomes. The visible stars and gas only account for a small fraction of the total. Most of the mass lies in the dark matter halo, which extends far beyond any star we can observe. Current estimates for the Milky Way's total mass range from roughly 1 trillion to 2 trillion solar masses. The uncertainty isn't small. Newer measurements keep revising the number, and the answer depends heavily on assumptions about how the dark matter halo is distributed. We live inside it, we measure it every day, and we still aren't sure exactly how heavy it is. In 2013, the European Space Agency launched a spacecraft called Gaia, and astronomy has not been the same since. Gaia's mission is to measure the positions, distances, and motions of stars with extraordinary precision. It has cataloged more than 2 billion stars. From that data, astronomers have mapped the three-dimensional structure of the Milky Way in greater detail than ever before, identified ancient stellar streams from long ago mergers, traced the warp of the outer disk, and measured the Sun's orbit to extraordinary precision. Every major data release from Gaia produces a wave of new discoveries that revised what we thought we knew. It is one of the most productive scientific missions ever undertaken. A quiet revolution conducted in the language of position, motion, and time. From inside the Milky Way, we can't see it the way a photograph shows it. We can't step outside and look at our own spiral. We're embedded in it, surrounded on all sides by the disk we're part of, and what we see ice a pale band of starlight crossing the night sky, nothing like the bird's eye view we imagine. It took centuries of observation, cataloging, measurement, and mathematical deduction to even understand that we live in a spiral galaxy, that our galaxy is just one of hundreds of billions, and that we are located in aqueous outskirts between major arms. We're still mapping it. We're still learning how big it is, how much it weighs, and how it formed. The galaxy we live in remains, in many meaningful ways, only partially known. The story of the Milky Way is also necessarily the story of how far scientific understanding has come, and how far it still has to go. And now, let the galaxy slowly recede. We've moved through all of it. The spinning arms and quiet halo, the stellar nurseries, and the shredded remnants of ancient collisions, the black hole at the center and the wandering stars at the edge, the invisible dark matter holding it all in place, and the impossibly old stars that remember a time before the galaxy had a shape. You are not just watching this from the outside. You are part of it. The carbon in your cells came from stars that burned and scattered billions of years before the sun existed. The iron in your blood was forged in supernova. The calcium in your bones was spread through the galaxy by dying stars and reincorporated into the cloud that became our solar system. Every atom that makes up your body has participated in this system. You are assembled from the Milky Way's own recycled material tonight. While you sleep, the galaxy continues. Stars are being born in cold, collapsing clouds 1,000 light years away. Pulsars tick steadily in the dark. The galactic center hums with X-ray radiation. The sun sweeps forward on its slow arc, carrying you with it. You don't need to do anything. Just rest. If tonight's journey felt worth your time, Next Worldwide is here whenever you need it. Consider subscribing. It helps us keep going. Sleep well.